students. Today we are going to learn about induction machine, equivalent circuit of induction machine. Last time we have discussed about the similarity and difference between induction machine and transformer. That induction motor and transformer have the same characteristics, with in induction motor the secondary winding or the rotor moves. Here is the primary winding or the stator, and here is the rotor or secondary winding. So induction motor have similar with transformer, with the exception that secondary winding or the rotor are free to rotate. In that case, the frequency and voltage also different. Now, when a rotor is locked or blocked, which means motor speed is equals to 0, slip is 1, as slip is equals to synchronous speed minus motor speed over synchronous speed. So motor speed is equals to 0 means slip is equals to 1, or the rotor is blocked by hand or some belt mechanism. And here is, in this case, the largest voltage and rotor frequency are induced, because here is induced voltage when slip is equals to 1, induced voltage is maximum and rotor frequency is maximum when slip is equals to 1 or the motor is blocked. On the other side, if the rotor rotates at synchronous speed, which means the same speed as motor speed, which means synchronous speed is equals to motor speed, slip is equals to 1. Here induced voltage and frequency in the rotor will be 0, since slip is 0. Here ERO is the largest value of rotor's induced voltage when the rotor is blocked or when the slip is 1. So for rotor frequency, the same is true for this. When the rotor is locked or blocked, slip is equals to 1 and the maximum frequency attained can be obtained in this case. And also the reactance, which omega L is equals to 2 pi FL, which means omega means 2 pi F, L means the inductance. Now the frequency of induced voltage in the rotor changes, the reactance of the circuit also changes. If the frequency is changed, the reactance also changed, both directly proportional with the rotor reactance, which means 2 pi SFE times L, since rotor frequency is equal to SFE, which means 2 pi FE LR means RO, which means the reactance at S is equals to 1. Now you can draw the equivalent circuit of the rotor as follows. Here is the induced voltage on the rotor, here is rotor current and rotor resistance. So the rotor current can be divided by the voltage induced on the rotor over rotor resistance plus JXR, where R is the induced voltage in the rotor and RR is the induced rotor resistance. Now IR can be determined from ERO over RR over S plus JXRO. Here is the equation of determining a rotor current. Dividing S with both sides on the numerator and the denominator, we can get ERO over RR over S plus JXRO, where ERO is induced voltage and XRO is rotor reactance at the rotor. When slip is equals to 1, we can determine IR is equals to ERO over RR plus JXRO. Now the rotor copper loss can be represented as per phase copper loss is equals to I square, or rotor current multiplied by resistance. And here is the equivalent circuit of a rotor when slip is different from 1. If slip is equals to 1, this slip should be eliminated. After that, now there are different types of loss occurring in an induction machine, because the rotor is freely rotated and there are friction plus windage loss or mechanical losses, and there are different types of loss: stator copper loss and rotor copper loss and core loss. This core loss can be subdivided into eddy current loss and hysteresis loss. Now to calculate these all losses, we can Draw the power flow diagram of the induction motor and determine from this power flow diagram. Now here is the input power in the stator winding. Here is the stator copper loss which is equals to stator current multiplied by rotor stator resistance. Here is the core loss, which can be divided into eddy current loss and hysteresis loss, and the air gap power here is used to induce the voltage on the rotor winding, which is rotor copper loss, which equals to rotor current multiplied by rotor resistance. Here is friction plus windage loss. Here is induced torque multiplied by speed, which is the power converted, which is mechanical power converted in the motor. Here is straight plus loss, and here is the output power, which is load torque multiplied by motor speed. The total output power derived from the motor. So this is the general power flow diagram of an induction motor. Now we are going to deal with each and every equation one by one. The input power is equals to square root of 3 line voltage multiplied by line current times power factor. So by multiplying both sides by square root of 3, we can get this phase voltage and phase current multiplied by cosine of theta. Here is the input power. And stator copper loss means this, since the machine is 3 times stator current multiplied by rotor stator resistance. Here is air gap power. The air gap power is equal to input power minus stator copper loss plus core loss. Here is air gap power. In this case, the power can be calculated by subtracting input power by stator copper loss and rotor copper loss. Then after that, we can determine the rotor copper loss. Also, rotor copper loss means the loss occurring on the rotor, which means rotor current square multiplied by rotor resistance. Now, we can determine the converted power from power and rotor copper loss. The output power is equal to converted power minus friction plus windage power. So the input power can be determined like this, and stator copper loss is determined from here. Now air gap power is equal to input power minus stator copper loss plus core loss, which finally divided by the slip. Now rotor copper loss is here, and the converted power can be derived from here. The converted power can be calculated as gap power minus rotor copper loss. Then finally output power here. Output power can be derived from here. Output power can be calculated from converted power minus friction plus windage loss plus stray loss. Here friction plus windage loss plus stray loss, and the induced torque, which is equals to the torque induced in this, which is equals to converted power over motor speed, and the load torque is equals to output power over motor speed. Now we can calculate this air gap power over motor speed. Here is the relationship between air gap power and converted power and rotor copper loss. So converted power is equals to 1 minus slip multiplied by air gap power, or air gap power is equals to rotor copper loss over slip. Now we can calculate or can work an example equivalent to the above equations. So a 480 volt 60 Hz 50 HP 3-phase induction motor is drawing 60 amp at 0.85 power factor lagging, which means negative, and the stator copper loss is 2 kilowatt, rotor copper loss are 700 watt, and friction and windage loss are 600 watt. The core loss are 1800 watt, and the stray loss are negligible. Find the following quantities. So first of all, before determining the air gap power, we can determine the input power, which means square root of 3 times line voltage times line current, and this is the power factor. So simply we get this 42.2 kilowatt, and the air gap power can be determined from input power minus stator copper loss. The stator copper loss is already given 2 kilowatts. So by dividing this, we can get, and the core loss is 1800. here 1800 watt, then we get this value. And the converted power, P converted is equal to P minus rotor copper loss. The rotor copper loss is already given 0.7 kilowatts. To change watt into kilowatt, we divide in 1000. Then output power is equal to converted power minus friction plus voltage. Then we can get the output power like this, and this output power have been changed into kilowatt or horsepower by dividing into 746 HP. Now power and input power is already calculated, and then we can determine the efficiency of the motor, which is 88%. So the machine, or this circuit induction machine, has the efficiency of 88% efficient. Now the next example here, a 460 volt 25 HP 60 Hz 4 pole Y connected induction motor has the following impedance in ohm per phase referred to the stator winding. Now stator resistance is given, rotor resistance is given, stator reactance and rotor reactance are already given. Then total rotational losses are 1100 watt and are assumed to be constant. The core loss is lumped in with rotational loss for the rotor slip of 2.2% and the rated voltage and the rated frequency. Find motor speed, stator current, power factor, converted power, and so on. This speed is the motor speed. Before determining the motor speed, we have to calculate the synchronous speed. Synchronous speed is equal to 120 supply frequency over P, and then 120 times 60 over 4. Since the frequency is 60 and the pole is 4, so here is the synchronous speed, and can determine the motor speed 1 minus s times synchronous speed, which means speed is already given and synchronous speed is already calculated. We can get here 1760 revolutions per minute. Now stator current. From this equivalent circuit, the stator current is determined by the phase voltage over divided by this equivalent circuit. So after that, calculating this R2 over S plus JX2, which means before determining current, we have to calculate these all equivalent circuits of the resistance. Now R1, X1, X2 and Xm are already given. Here R2 over S and JX2 are in series. Reduce all the equivalent circuits and then after that determine the stator current. So these elements R2 over S and JX2 are in series. Then this Z2 means R2 over S plus JX2, which means R2 is already given and JX2 is already given, slip is already given, so we can calculate this value since these two elements are series. So we can get 50.1 at an angle of 1.76 degrees. So this is the secondary impedance, which means JX2 plus R2. Now this value is in parallel with this value, and ZF is equals to, since the two elements JXM and Z2 are in parallel, ZF is equals to 1 over JXM plus 1 over Z2. So substitute all the values. JXM is already given here and Z2 is already calculated here. Substitute this value and this value, we can get this 12.94 at an angle of 31.1 degree. So now ZDF is already calculated, and after that all these values are represented as ZF. So all these values are reduced and are connected in series with these two components. These are stator resistance and stator reactance, and these components are stator components. This is a magnetizing component. Now R1 plus Jx1 is Z stator. So Z total is equals to Z stator plus ZF. Now here is the equation after this is ZF and this is Z stator, which means R1 plus Jx1. So Z total is equals to R1 plus Jx1 plus ZF. Now R1, which means 0.4641 plus J X1 1.106 plus 12.94 at an angle of this, which means this is a ZF. Now we can get, after that, we can get 40.07 at an angle of 33.6. Now we have already calculated the total impedance and the line voltage is already given. We can get that the stator current is equal to phase voltage over total impedance, which means phase line voltage is 460. To change it into phase voltage, it is divided into square root of 3, since the motor is connected in star. If connected in delta, the motor is the motor voltage is equals to phase voltage is equals to line voltage, but or connected in star, so we have to divide with the square root of 3 to change phase voltage. After that, we get 80.88 at an angle of minus 33, which means a lagging power factor, this negative value. So the stator current is already calculated here. 18.88 is the stator current, and the power factor means, second question, power factor is cosine of this value, which is negative value, shows the lagging power factor. Now to calculate the converted power and output power, we have to calculate the input power and stator copper loss. So the input power is simply calculated as square root of 3 times line voltage times line current cosine of theta. So this value is the input power calculated. Here is stator copper loss, which is equal to 3 times stator current times stator resistance, and you can get this value. And here is the air gap power. Air gap power is input power minus stator copper loss, which is equal to 11,845 watt. After that, we can calculate the converted power. The power converted into mechanical is equals to 1 minus S. S means slip. It's already given 2.2% times air gap power. The air gap power is already given here. So 1 minus S multiplied by this is the converted power. So by multiplying this value, we can get the converted power. Then after that, we can calculate the output power. Output power can be calculated as converted power minus friction plus windage losses. So here is converted power. Friction plus windage is already given here. The friction plus windage is already given at 1100. Then finally the output power can be derived like this, and after that, to change into horsepower, we simply divide in 746 watt. So we can get 14.1 horsepower. Then the torque induced from the power flow diagram calculated above, torque induced is equal to air gap power over synchronous speed, which means air gap power is already calculated here, and synchronous speed is 1800. To change this into rad per second, this 1800 is represented in revolution per minute, and torque induced should be calculated in Newton meter, and we have to change it in rad per second. So to change in rad per second, we have to multiply to pi by 60. Now here is the induced torque, and the load torque also same is true for induced torque, but the only difference that in induced torque we have used the synchronous speed, and in load torque we have used motor speed. So 1760 is represented in revolution per minute, and 2 pi over 60 is used to change the revolution per minute into rad per second. After that, input power is already determined and output power is already determined. Efficiency of the motor in this case can be determined, that output power over input power multiplied by 100%. So can get 83.7% efficiency. So this motor or three-phase induction motor connected in star having this parameter have the efficiency of 83.7%. So thank you for watching. If you like this video, please share and subscribe.